All right. Today is the last day of new material for Physics 213. So if you're never going to take another physics course again, this is it. This is the last bit of information that you get. Just as a review, today we are covering, we finished oscillation, so all we've got left is sound. Tuesday and Wednesday are review. The Russian review system is we do 3 days of new material, 2 days of review, and then a test. And then on Thursday, we have test 3. On Friday, we do our final review. And then on Monday, we have the final. So a week from today, it will all be over. And then for those in 214, enjoy your 2-day holiday. And then we all start it all over again on Thursday. Copies of test 3 from 2 different semesters are currently online. As usual, we will do one of them tomorrow and then the other one on the next day. All the problem sets are out. We're good to go. So let's begin with this. On Friday, we covered oscillations. And with oscillations, we had 2 types of pendula. The simple pendula and then the spring pendula. And with these type of oscillations, if we were to plot it out, they both use time as the horizontal, if we're just thinking about their position. But for a simple pendulum, it's angle theta. So you have the 0 angle, and that's theta, and then that could be theta. And so if you measure it as a function of time, it goes back and forth. And then the time between there and there is called the period. In a spring pendulum, it is the displacement x. So if it's to the left, if it's compressed, we say it's negative. If it's to the right, it's positive. And so if it's bouncing back and forth, x would be on the vertical and t would be on the horizontal. And once again, the times between either peak to peak or trough to trough, we call that the period. Now, in the case of well, no, that's not right. We'll just do this now. What sound is about is that there is once again a time, and then on the vertical you have the change in P, the displacement and pressure. On average, the pressure in this room is about 1 atmosphere. But what is sound? Sound is I'm passing air over my vocal cords, and the vocal cords are causing a slight change in pressure. And that high-low, high-low, high-low change in pressure that you encounter on your ears interpret that as sound. So if the pressure differential goes up, down, up, down, up, down, up, down, up, down, that's a high pitch, a high frequency. If it goes high, low, that's a lower frequency. So that change in pressure and its repetition makes a difference on what pitch sound you hear. Because when you're thinking about it biologically, the sound impacts your eardrum. The eardrum causes I always forget but I don't study anatomy. The 3 bones in your ear that are then hooked up to your cochlea or whatever, and then the little hairs vibrate and they send nerves, all that stuff. And why did I do a bad job? Because I'm a physicist, not a biologist. But getting back to the point, with sound, if you were to measure the pressure at a particular point, P0 is the background average pressure, and then the change in pressure is what you're measuring. This is, once again, the period. Now with sound, we add another little change to what goes on. If we plotted the change in pressure as a function of position, let's just say for a moment that we all have the ability to control time and to stop it and then study it. As the sound is coming out of my mouth and then I stop it, if we were able to see those sound waves, we could see small regions of high pressure or higher pressure, and then regions of lower pressure. And this pressure can be marked, and then this difference is called lambda, and it is the wave length. And remember that we also have heard of another lambda, and we're going to need to be careful about recognizing when lambda is associated with wavelength and then when lambda is associated with linear mass density. So there are 2 lambdas in there. There is a relationship in sound with its wavelength and its frequency. The velocity of sound, which I'll say is v sub s, is lambda times f. That if you took the frequency of the wave, multiplied it by its wavelength, you would get the velocity. In fact, this equation is useful for all sorts of waves. Wave in a tidal pool, or wave in a pool, sound waves, light waves, all sorts of waves follow this relationship, that the velocity is equal to the wavelength times its frequency. You could also say that because f is 1 over t, that the velocity is lambda over t, where that is its period. So as a simple example, you are in a wave pool. You bob up and down 10 times in 30 seconds. The waves are 20 meters apart. What is the velocity of those waves in the pool? So we have a couple of equations that we need to use. One is that v sub s is equal to lambda f, and that the total time is the number of oscillations times its period. Now we could rearrange this in all sorts of ways. We can get the period to be the total time divided by the number of oscillations. 1 over period is n over t. We're just taking the inverse. And 1 over t is frequency. So we write that out. Substitute it into there, and then lambda is equal to n divided by total time. The waves are 20 meters apart. Its wavelength is 20 meters. So 20, n, you bobbed up and down 10 times. 30 seconds. So it's 1/3 of 20, or 6.67 meters per second. And that's how you do some basic manipulation of waves. A very legitimate appetizer. Now with test 3, in terms of the appetizer, I don't really know what it's going to be. Unlike, you knew test 1 was going to be a conversion. Test 2 was going to be right-hand rule. 3 is kind of I don't know what I'm going to do with that. It's going to fill in a gap somewhere. In the lab, VS will be determined. We're going to go over that experiment in a little bit, but not right now. I will say this at the moment. In the lab, VS will be determined. It is about like 343 meters per second. It's around there. It is temperature dependent. It can vary. Hot day, cold day, it'll change. In Physics 2:13, we're keeping things simple. V of S is equal to 350. The reason why I'm using V sub S is equal to 350 is for a wide variety of reasons. The first of which is it's the same reason that I use 10 meters per second as gravity. It's an easily divisible number. I can handle it really easily. I just use it as a constant. Here in this room and in the homework, it's 350 meters per second. Over there in the labs, it could be all sorts of numbers. So if he gives it to you, thank them. If they don't give it to you, you're going to have to figure it out. There are, I'm trying to think of the next step. In Physics 2:13, you can produce sound in several ways. There are 3 ways to make sound in 2:13. One is a string. One is a pipe, and the other one is called a half pipe. And we will go over all of these. A string has a length L, or actually the length that I'm trying to think of yeah, we do use that, is capital length L. These two are fixed points. Those fixed points, think of it like you got a clothesline, the mounts on either side of the clothesline attached to the wall, a tree, a house, whatever. Those are fixed, and then you pluck the string, and then it causes a vibration because the string is moving against the air. The pipe also has a length L, and depending on, there's all sorts of instruments. I mean, namely, you could just take a tube and blow across it, and it will create a sound. And then there is a close cousin to the pipe, the half pipe. It's my name for it. A lot of people just call it a pipe closed at one end. I say, half pipe. 2 syllables is a lot less than however many syllables a pipe closed at one end is. But in all 3 cases, from end to end, that length is L. What we're going to do now, for the time being, is talk just about the string. What I need you to do is think about the string can vibrate like this, where there are 2 fixed points no movement, and then there is 1 point that moves the most. Those 2 points move the least. This point here moves the most, and then all the other points move lesser and lesser. And a lot of times what I do when marking this down is I use the string and I write that out. And then the point at which it moves the most, I write an open circle. So for fixed points, I write closed circles. For the points that move the most, I write open circles. These fixed points, the closed points, I call them nodes. Nodes are fixed. Nodes don't move. Nodes don't change. Here, the points that move the most, they're called antinodes. They move the most. Quite a few of your multiple choice will be, you have a string, how many nodes are in it, how many antinodes are in it, and discuss it. There are many other types of, and this is what they end up calling a standing wave, or a resonance. A standing wave or a resonance is a time at which you can kind of think it, I think of it as just a ringing. You just see it do something just clean. Now, when you and your friend are just swinging that rope back and forth or up and down, most of the time it's noisy. There isn't a coherent shape or form to it. And then at one particular frequency that you're sitting there swinging that rope, the rope will suddenly do up, down cleanly, where there is only one point that is moving the most and everything else is following it. And then you start shaking it a little faster, and then it goes back into its noisy situation. And then the rope does this. It hits another harmonic. It hits another resonance, where the string bounces up and down in a rhythmic fashion, in a controlled fashion, in a non-noisy fashion. And here there are 3 nodes and 2 antinodes. Whereas here, there are 2 nodes and 1 antinode. So you keep shaking faster and faster. And what you find out are there are many types of resonances. There is this. There's that. And then there's that. And so on. But really all we're going to do is study the first 5. So those are the nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes. Here, 2, 3 antinodes, 4 antinodes, and 5 antinodes. And putting in the hollow points. Because what's going to happen on the test is I'm going to, on the, if I don't remember to put it up on the test, I'll put it up on the whiteboard. But I will draw these pictures with the nodes and antinodes, leave them all unmarked. And then you'll be given a list of questions in the multiple choice asking you which one has 4 nodes, which one has 2 antinodes. And then you refer to the diagram and you let me know which one it is. These have labels. These have what we call N, or harmonic number, or its resonance. And they are given in the order in which they occur. This one, N is equal to 1. This one, N is equal to 2. N is equal to 3. N is equal to 4. And N is equal to 5. That just gives you the order in which they occur. You can associate the harmonic number with the number of antinodes. N equals 1, 1 antinode. N equals 2, 2 antinodes. N equals 3, 3, and so on. So if I said N is equal to 4, how many antinodes are there? You would say 4, because the number of antinodes is equal to the harmonic number. If I said how many nodes are in a wire that's vibrating at N equals 4, you just merely add 1. So number of antinodes is equal to N. The number of nodes is equal to N plus 1. There is a naming convention that these strings use. There is what I call the harmonic system of naming, and then there's what I call the overtone. In the harmonic system, really all it is the nth harmonic. So if n is equal to 1, it's the first harmonic. N equals 2, the second harmonic. Third harmonic. Fourth harmonic. Fifth harmonic. The overtone system is another way of describing these same tones. It's using a different way of naming. The overtone system, the first harmonic, is what they call the fundamental frequency. It is the first frequency at which this thing resonates, and so they name it the fundamental frequency. N equals 1, is it first harmonic or fundamental frequency? It can be either. Now, once you pick the harmonic system, you tend to stick with the same naming convention. If you pick the overtone system, you tend to stay in that overtone naming convention. The first tone over the fundamental frequency is called the first overtone. The first overtone is the first resonant frequency above the fundamental frequency. The third harmonic is the second overtone. And then third overtone, and then fourth overtone. So these naming conventions are pretty easy once you figure it out. If it equals 1, you go, if it's the harmonic system, N is equal to whatever harmonic you're dealing with. And then for the overtone system, N is equal to N minus 1 overtone if N minus 1 is equal to 0, then it's the fundamental frequency. If I know that N equals 1, I'm dealing with the fundamental frequency. I don't need to subtract 1 from it and do all that logic. But if you need all of that extra stuff, then go have fun. All right, so we've named our resonant conventions. We've figured out that we've looked at the nodes and the antinodes and the way that they physically vibrate. Let's get into some equations. The frequency that this thing resonates is NV over 2L, where N is the harmonic, V is the velocity of wave in string, and L is the length of, and I'm going to clarify this, vibrating string. So the frequency is NV over 2L. In a string, the V is not 350 meters per second. We're not talking about sound in air. We're talking about the oscillations in a string. That this is equal to T over lambda, where T is the tension and lambda is the linear mass density. T is the tension, lambda is linear mass density. Let's put these two together. Frequency is N over 2L T over lambda. And so that is the resonant frequency of a string. Now, a couple of questions. We're all human. We've all been outside in the real world, and we've all seen a guitar. And we've all seen a piano. On a guitar, which strings have the lowest frequency? The big fat strings or the little tiny strings? The big fat ones have the lower frequency. You said you went that, and that to me means small.
Yeah, I was wrong.
You were wrong. Okay, excellent. All right. First off, biggest piece of advice, the first step to wisdom is to admit when you're wrong. Very nice. Very good. Now, the big fat strings have a large what? They have a large diameter, which means they have a large, yeah, which means it has a large, compared to a small string, it has a bigger linear mass density. There is more mass per unit length. So the big fat strings are the lower frequency because lambda is in the denominator. If lambda increases, frequency decreases. When you look at a piano, the lower frequency strings are on the left, the high frequency strings are on the right. If you had, the best example are the baby grands or the grand pianos. Those have the short end of the, I'm sorry, I'm gonna get to that in a moment. The thin strings are on the right, the higher frequencies. The thick strings are the lower frequencies. And if you ever pluck a really wire thin string, you get a really high tinny noise. You pluck a big lower string, then you get a lower frequency. Also if you notice with bass guitars have produced very low sounds, so they have very thick strings. Next question. You're tuning your string, and what do you do to cause the string to increase its frequency? You increase the tension, you tighten it down. So by increasing tension, that frequency goes up. If you loosen the string, you lower the frequency. If you tighten the string, you increase the frequency. Like if you tighten the string on a guitar, you hear them tune the guitar and they pluck it and then they tighten it and you hear this. What's happening is they're increasing the tension, the frequency of the string increases, and so it resonates at a different pitch. You also know that if you increase the length, the frequency goes down. If you look at a piano, the bigger strings are the lower strings are on the left, and they are longer. With guitars, they make more of a difference in string length density, so that's why the strings aren't that different. And also, one of the things that you remember is when you're playing a guitar, your fingers on, I don't play guitar, so what the neck of the guitar, when you're changing chords, what do? You place your fingers on a closer to your right hand or a point further away from your right hand. If you move your fingers away from your hand, you're increasing the length, you're decreasing the pitch. If you move your fingers closer to your hand, you're increasing the frequency by decreasing the length. Another thing about the tension, if you know guitar, you got the whammy bar, the little bar at the end where you can just sit there and just go wah, 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 wah. That's really what you're doing, is you're changing the tension slightly, and that causes the frequency to change. So let's first do a simple string. So string of length L is 2 meters. It is at its second overtone. So if it is at its second overtone, what is its harmonic in value? I just got done telling you. 3. The moment I say what harmonic or overtone it's at, you immediately know what in we're dealing with. The question that I want to know is, what is the tension if over this 2 meter string, the mass of the string is 20 grams? Do I have everything? No, I need a frequency. Frequency is 800 hertz. So you pluck a string at its second overtone. It emits a frequency of 800 hertz. The mass of the string is 20 grams. What is the tension? And we get this. First, write your frequency. F equals NV over 2L. And V is tension over lambda. And lambda is MS over L. So plug these two in together, you get V equals square root of TL over MS. Lambda is in the denominator, so 1 over lambda is L over MS, and you get this. Plug those two together. F equals N over 2L square root of TL over MS. Square it. F squared, N squared over 4L squared. Oops. Oh, crud. Hold on. When squaring both sides, you've got to square what's under this. So one of the L's cancels, and I'm left with is equal to that. So this gives me 4, 2, 800. Now MS, remember, we're dealing with our fundamental units. What is the fundamental unit for mass? Kilograms, not grams. So the number that we plug in is 0.02 kilograms. So we get that. And so I get a tension of 11,378 newtons. So I would take 11,300, I would take 11,380. That's enough. Now a lot of you could say, well, that's a very high tension. Wouldn't a 20-gram string break under that force? String's made out of Rebellium. Rebellium can handle any amount of tension placed on it. So let's not worry about that part. Now, the next step, vibrating strings are pretty easy to handle. One of the questions that crops up is, Dr. Eschenberg, did you say that on every single test there will be an Atwood's machine problem? My answer is, yeah, there's going to be an Atwood's machine problem on every single test. And so the next question is, well, we've been studying sound and oscillations. How can you put an Atwood's machine problem in a test dealing with sound? It's quite easy. Let me show you. It's called an Atwood string. This will be on the test, kids. An Atwood string is a variant of just a simple vibrating string. It sees if you're paying attention. It adds an extra layer of understanding to sound, string, line density, and that is, you have a pulley, and looped over the pulley is a mass, and it's just hanging there. And looped over the pulley is a string, and the string is attached to the wall. There is a L1 and L2. In this particular case, L1 is the vibrating part. L2 is the non-vibrating part. And the total length L is L1 plus L2. In this particular problem, what we're going to do is I'm going to say that L1 is equal to 2 meters and L2 is equal to 4 meters. The mass of the string is 20 grams. I want to know how much mass is hanging on that string. If its second harmonic, if its frequency is 600 hertz. So the Atwood string is a little bit different. Technically, it's not an Atwood's machine, but it satisfies my desire to always have an Atwood's problem on the test. A problem like this will not be on the final because I've got real Atwood's machines to play with. So given all this information, how do I get the mass out of this thing? And when I'm talking about mass, I mean the hanging mass, not the mass of the string. Well, you've got frequency is NV over 2 lambda, or L1. L1 is in the position of the vibrating length. A lot of people would put L2 or big L. Well, big L is the total length of the string. It's not vibrating over the entire length of the string. It's not even vibrating over length 2. If you plucked the L2 part of the string, the mass would just go back and forth and not really do anything useful. Plucking the L1 part of the string does make it vibrate at our desired frequency. And so you get this. Well, V is tension over lambda. Now let's go with lambda is equal to the mass of the string divided by the total length, or mass of the string divided by L1 plus L2. The tension is provided by the hanging mass. Technically it isn't a fixed point, but what it is that pulley has a little, and the string just goes in there. So you can treat it like a fixed point, but the tension in the hanging mass is providing the tension for the rest of the string. You can use this to show that the tension in the string is mg. And this is the hanging mass, not the mass of the string. So V is mass that's hanging times gravity over lambda, which is ms L1 plus L2. Plug that into there. So F equals N over 2 L1. And you get this. This is the general solution. Once again, I'm going to pound away at the idea of alphabet soup is superior than plug and chug, because you can do this. Atwood string is going to show up on the test. It is a metaphysical certainty. All of the problems in this test will break down into getting to this formula, a formula that you must derive. Now, I can ask for anything in that formula and get you to solve for it. I can give all sorts of weird substitution things, but you should be able to do any of this and solve for it. The only one that gets a little bit tricky is solving for L1, but I would have to give you a little bit more information. The relationships that you need to think about this are that L1 plus L2 is equal to big L, and you can also say that L1 is equal to L minus L2, or that L2 is equal to L minus L1. So you may end up having to know these and plug them in. So let's solve for the hanging mass. You got to square it. And so you get that. Now solve for hanging mass. And you get that. Now plugging in the values. Remember that the mass of the string needs to be in kilograms. And you get 480 kilograms exact. Once again, another advantage of using the alphabet soup method is that you will get the most accurate answer. You will also get whole numbers if Dr. Eschenberg has thought ahead in the game and worked out so that the numbers work out correctly. Or give you a number that is beneficial. And so that is the Atwood string problem. What I would do is I would understand how to derive that equation and then be able to derive for every single variable within it. And so that's the Atwood string. So the string problem is going to be this. The pipe problems, which tend to be a little bit more the pipe problems are going to be more towards multiple choice. They're going to be one of the pipe problems is very important because it's going to be in the lab are half pipes and full pipes. The full pipe is length L. Its resonant frequencies are NV over 2 big L. And for string and for full pipe, those ends go 1, 2, 3, etc. So the full pipe, you get this. N is the resonance number. L is the length. and V is the velocity of sound, so I can just write that. And Vs is equal to 350. On the test, it will be 350. So, as an example, third overtone. If frequency is 800 hertz, what is L? Easy to solve. Take that. L is NVS over 2F. N is what? Third overtone. 4. 350. 2 times 800. So it is 1400 divided by 1600, or 0.875 meters. And so that's just a simple pipe problem. Now, half pipes take everything and just mock it. It comes from the derivation that we're not going to go into, but a half pipe, its ends are a little bit different. From the way it is derived, the ends are 1, 3, 5, ... Even odds, or even odds, what was that? Even ends do not exist. It is going to be, it's one of the, there are 2 or 3 of them that are in the multiple choice bank, so some of them always creep in. You have a half pipe resonating at its second harmonic, N equals 2. What is the frequency that it's resonating at? Answer, it can't resonate at its N equals 2 harmonic. Now there is a little bit different. With this, hold on, let me go back. With this naming convention, these are for strings and full pipes only. The naming convention for half pipes get a little bit different. So for harmonic and overtone, the numbers go 1, 3, 5, 7, 9, etc. The harmonic system is just based on its in value. So first harmonic, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, etc. So in terms of the harmonic naming convention, second, fourth, sixth do not happen. In the overtone system doesn't really care. Its definitions are the first resonating frequency is its fundamental frequency. So the fundamental frequency is the first overtone for either system, string, full pipe, half pipe. Its definition about overtones, its first overtone is the first resonating frequency above the fundamental harmonic. So the first overtone is the third harmonic. The second overtone is the fifth harmonic. The third overtone is the seventh. Fourth overtone is the ninth. So you can have a second overtone for a half pipe, but you cannot have a second overtone for a half pipe. The second overtone on a half pipe is 5. The second overtone on a full pipe is 3. So understand the differences between those two systems. The naming conventions are a little bit strange, or they differ from each other. So the last, the problem with half pipes that we're going to talk about is your lab. Your lab equipment is it's a tube. There is a stopper at the bottom. There's a tube that comes out of that stopper, and you get a big jug of water. For easy motion of water in the tube, open the cap. If you don't open the cap, there isn't, it doesn't allow pressure to change the fluid's position. So you've got to open, you just got to crack it open a little bit so that the air can get in there. If you raising the bottle causes water to flow into tube. So basically the water inside will go up. If you've got this tube lowering the bottle, causes water to flow into bottle. And if it flows into bottle, that water level will drop. So if you raise the bottle, the water in the tube rises. If you lower the bottle, the water flows out of the tube. This means that in this situation, L decreases. And in this situation, L increases. L is the length from the top of the tube down to the water level. The water in the tube acts like the closed end of a half pipe. So that's the closed end, that's the open end. The frequencies at which it resonates is NV over 4L, where N is equal to 1, 3, 5, etc. So you're changing the tube length effectively by changing the bottle's position. If you raise the bottle, you're lowering the effective length of the tube. By lowering the bottle, you're increasing the effective length in the tube. Those are the frequencies. Now what happens is they're going to want you to get this water near the top So you're going to have your little bottle up here with very little water because all the water has flown into it. And they're going to give you a tuning fork. There will probably be, that's a horrible spelling. Tuning fork. There will likely be only 4 stations in the room. So they'll have you divide up into groups of 4 or 6, depending on how many people are there. They'll give you an assortment of tuning forks. Now what you do is you take your tuning fork, they'll give you a mallet. Trying to think where those oh no, the tuning forks are in the lab, so I'm not going to go back there. So the tuning fork, what happens is you take your mallet and you thunk your tuning fork and you hold it over the open end of the tube. And when you do that, you lower the bottle. And so what happens when you lower the bottle? The length starts changing. Now, a couple of words of advice on those tuning forks. The real way to take a tuning fork is to initially take that tuning fork. The mallet they give you is this little rubber thing on the end of an aluminum mallet. What's the best way to do it, in my opinion, is to take it and just bang it off your patella. And that'll really, well, it'll slightly hurt, but it'll really get that tuning fork to ring well. And then what you do is the tuning fork itself. The problem with the tuning fork and banging it off your patella is that the sounds get a little bit muddy. There'll be other harmonics. So if you've got a tuning fork that resonates at 440, there's going to be an 880, there's going to be a 1320 rattling around in there. You're going to hear multiple tones. And so what you do is you take your fingers and at the base of that tuning fork, just go tap, release. Just hold on to it for just 1/10 of a second and then release. And what that does is it dampens out the higher harmonics and gives you a clean tone. Once the water gets low enough to the resonant level, you take that tuning fork, you hold it over the pipe and you let the water fall. And then what you hear is something like, if where this Elmo is at the resonant level, what would happen is as the water falls, you just hear a when it hits that resonant level, the volume increases. And it's something that, I mean, right now I can look at you and see what you're thinking. I don't believe any of that. He's just weird old man at the front of the room. But when you hear it for the first time, that it'll just resonate. And some people, if they've got the tuning fork with enough oomph to it, I have actually seen the water vibrate a little bit. There'll be a little bit of like misting, little droplets kicking up in the air. That's because the frequency, when it resonates hard enough, it can move the water in the tube. So what you do is you're going to have like 3 tuning forks. So you're going to get 3 frequencies. And then you're going to get pick up the first, or I'm sorry, it's not like that. The first 3 harmonics for each of these. And then you're going to register those positions. From each of those positions, you're going to get a velocity of sound in air. You then get an average velocity for each of the frequencies, and then you get that total average for the velocity of sound in air. So in this experiment, You're supposed to determine the velocity of sound and confirm it. What's going to happen is the TA is going to give you the temperature of the room. They're also going to give you the equation to determine the speed of sound in air. So you take that temperature, put it into the equation. You're going to get a number around 343, I think. And then these values should be hovering around 343. You confirm it, and then you get out. Velocity of sound in air is about the easiest of the labs that you can do. The difficult part of this lab is, why do you not know where the positions in the tube where it'll resonate? Because you just started. Let me give you a helping hand on where to figure this stuff out. If you've got F equals NV over 4L, you can rearrange this. 4L equals NV over 4F. Now let's say for an instant that the speed of sound in air is 343. Let's just assume that for the moment. And you're looking at your tuning fork, and the frequency of that tuning fork is 440. What this technique does, and I've never seen it before until I started teaching it. Most everyone just starts at the very top and then just lets it fall. There's no need to do that. It's a waste of time. The tuning fork will, for a practical purpose, the tuning fork will only vibrate at a reasonable volume for 20 seconds, 10 seconds at a really good clip. So what you need to do is you need to approximate where this resonance is going to occur. We know we're on Earth. We know that the speed of sound in air is roughly 343. So let's just figure out kind of where it should be in the ballpark. So for n equals 1, L is 1 times 343, 4 times 440. Now for the other tuning forks, you replace 440 with whatever they give you. And you get 19.5 centimeters. The tube itself will be measured in centimeters. Now, when you do your calculations, you'll keep it in meters. One of the other things that we could do is we'll make the observation that if n equals 1, L is V over 4F. So for n equals 2, we could rewrite this as NF1. NF1. It doesn't really matter. V over 4F is the length associated with the first frequency. So you could take that 19.5 and multiply it by 3. And so that gives you 58.5 centimeters. And then 5 times 19.5 is 117.5 centimeters. No. Let's do it with the calculator. 97.5. So there is no point, there's no reason to search at 5 centimeters from the top. There's no reason, it won't happen. So what you do is for the first one, you know that it's going to be there, and so you start at about 16 and then you stop at about 22. So it's much easier to search over 6 centimeters than it is to search over the whole length of the tube. And what you do is you lower it and it goes past 19.5 and then you rock it back and forth. Now it most likely won't be at 19.5. We're kind of approximating the speed of sound in air. but it should be right around there. So just lower it, raise it, lower it, raise it. And then what'll happen is you'll hear kind of the broad band of the resonance, and then you start fine tuning it by rocking it back and forth with less change in depth, and then you'll get a better estimate. And then you do the same thing for 58.5 and 97.5. Let's say for an instance that the tube was only 80 centimeters long. You could find the 19.5 resonance. You could find the 58.5 resonance. But if the tube is only 80 centimeters long, the 97.5 resonance is not going to occur, so it's okay. You can skip that. If it's physically impossible to find, you don't have to worry about it. And so that's all that it is for the speed of sound and air problem. And so those are the types of sound. Pipe, half pipe, string. String will be Atwood string. Most likely you're going to get pipes either, well, you're definitely going to get pipes in multiple choice. It could be an appetizer. I haven't decided. All right, the last subject that we need to talk about for 213. This will be on the test, probably on the final. Doppler shifting. In Doppler shifting is you hearing a sound that changes depending on your relationship with a sound source and the motion of you and the sound source. There are derivations to this. We're not going to bother with it. The best example is you standing. You've got a cop car that is broadcasting sound and it's heading at you. So what do you hear? You hear a pitch that is high. As the cop car goes by, you hear a low frequency. So what you do is you hear the car and it goes, typically, I mean, you hear it even with cars. They don't even need a siren. You hear that, whoa. That's Doppler shifting. So what's happening? In Doppler shifting, the car is moving with the forward waves. So if you were to see the sound waves of a car that's moving in the direction of the sound, they're kind of bunched up because as it's producing the sound, it is moving with them. So if, let's say for an instance that sound moves at 2 steps per step, I emit a sound wave. If I was just standing here emitting sound waves, it would be like whoom, whoom. And if I moved with the wave, the distance between those waves in the forward section in front of me are closer. They're bunched up. But if I'm moving forward and sending sound backwards, emit a wave, step. That wave has moved back. Now I emit another wave, step. That one moves back too. The waves are further separated behind than they are in front. So you get a bunching up in the front and a spacing out behind. What happens when sound waves more frequently encounter you? You hear that higher frequency. What happens when you deal with, you emit sounds and they're further apart? You hear a lower frequency. Neither of which is the source of the sound. They're a changed value. There's also the example of, this one tends to, the moving source is a little bit weird. The moving observer, my explanation tends to be a little bit. Say you're surfing and you're moving in the opposite direction of the waves. The waves are coming at you and you are surfing into the waves. You are encountering those waves more quickly because you're just racing against them. If you were standing there just bobbing up in the ocean, the frequency of the waves hitting you would be as normally intended. It would just be bob, bob, bob. But if you're swimming against the waves, you're encountering the waves more quickly. And so the wave frequency goes up. If you travel against the waves, like you're trying to catch a wave to surf on it, the frequency of waves encountering you are less because you're swimming with the waves. Now, granted, you're not swimming as fast as the waves, so the waves are still overcoming your position, but they're overcoming it at a lower frequency. And so this lower frequency we perceive as a lower sound. So there are two major types of Doppler shift problems. There's the moving source. There is the moving observer. This is the case of a moving source. This is the case of a moving observer. So the moving observer is the surfer and the waves. The moving source is the police car passing by the observer. Now, there is the case of towards and away. Here, the car is moving away from the observer. Here, well, here it's moving towards, there it's moving away. So if the distance is getting less, it's towards. If the distance is increasing, it's going away. Here, the observer is moving towards the waves. Here, the observer is moving away from the waves. So what I'm doing is, there are 4 potential equations that you can have for this. Each of these changed frequencies, we use f prime. So the frequency that you hear is f prime. F is the frequency of the source. In the case of the moving source, there is going to be a numerator and a denominator. This is just the way that it's derived. In the way of a moving observer, it's entirely in the numerator. Each of these blocks there is a 1 and a V over Vs. Now, this is just because of the way that it's derived, and there are physical reasons why it's set up this way. But what I want you to do is think about the expected values. There's going to be a plus or a minus in each of these, and I need you to figure out which one is the plus and which one is the minus. Let's handle observer towards. So observer towards, I'm looking at this one. An observer towards hears a higher frequency. In fact, each of the towards hears a higher frequency. So F prime will be greater than F. Away, you will hear a lower frequency, F prime less than F. So if F prime is going to be greater than F, should that be a minus or a plus? Should be a plus. Because 1 plus anything will give me a number greater than 1. A number greater than 1 times F will make F prime greater than F. So understand these numeric relationships. Take a number, multiply it by a number greater than 1, you're going to get a number that's bigger. Observer away, that uses a minus sign because you need a number less than 1 so that when you multiply it by F, F prime is less than F. So for a moving observer towards, you use this. For a moving observer away, you use this. Now, moving source towards and away, once again, the moving source towards is going to produce a higher number. Should the denominator use a plus or a minus number? Or plus or minus symbol? Should use minus. Because if that's minus, this number in the denominator is going to produce a number less than 1. A number less than 1 in the denominator is going to produce an overall number that's bigger, thus ensuring F prime is greater than F, which means that that must be negative. And so these are the 4 relationships with what goes on. Let's do a simple problem. We'll do a moving observer. Oh, yes, thank you. And why should it be plus? Because you want a number greater than 1 in the denominator so that the overall number becomes less than 1. Thank you. We have an example. Train station. Siren has a frequency of 2,000 hertz. A train with you on it approaches and then passes by. What So what frequencies does it hear? So there's going to be a case where the train approaches the station, it reaches the station, it passes by. So it's also going to hear the that Doppler shift. What frequencies does it hear? And the one thing that I need is the velocity of the train is equal to 30 meters per second. It's a moving observer. What frequencies does the train hear? So you're going to have to use those two. The F prime, as it's moving towards, is equal to F1 plus V over Vs. So that's 2001 plus 30 over 350. Oh, helps if you use the right key. 2,000 times, not plus. 2171 hertz. So that is the first frequency. That's towards. Now the frequency away, (2001 minus 30 over 350). And I get 1829 hertz. So those are some simple Doppler shift problems. Now what we tend to end all the new material with is a form of problem that frequently ends up on the test or the final. And that is a variant of what I'm about to tell you. Whenever I go to a casino, I love to go to the roulette wheel table because there's a whole story about why it is what it is. In casinos today, when you put the ball, when the dealer puts the ball in play, all bets stop. You're not allowed to bet. Also, what you notice is on a roulette wheel table, there is an acoustic barrier between the wheel and the players. It's about 2 feet high, clear, about ½ inch thick, runs the length. Like you can't just put your hands into the play area, only the betting area. And then the other thing that you may notice is that on the wheel that there are these little nubs, like diamonds, scattered over the wheel. It is because of what I'm about to tell you. Back in the mid-70s, you were allowed to make your bets while the ball was in motion. The moment the ball fell from that edge, betting stopped. But while the ball was in motion, you could still make bets. It didn't have that barrier between the roulette wheel and the bettors. And it also didn't have those little nubs. It was a very smooth surface. A bunch of physics grad students from the University of California at Santa Cruz figured it out. Now granted, what they did was cheating. So much so that when the casinos found out what they did, they said, well, if you want a real broken arm, you can just step in the back with us and we'll make it happen. What they did is they got an actual casino grade roulette wheel. They took it up into the attic of their house where they were living for the summer, and they played roulette all the time and figured it out. They had a problem. They had an issue that they need to figure out. The dealers frequently are bored, and they will always usually spin the ball at the same velocity. And what's really interesting about this story is I was dating a girl. We're down in Biloxi. We're standing in the casino, and she asks me, what does physics do for me? And I turned over to the roulette wheel table and I said, come over here, let me show you. And I told her this and the dealer's looking at me like, uh-oh, this dude knows. Now, I can't bet worth for snot, so I was harmless. But he knew that I knew what was going on. That ball was moving towards the player and away from the player at the same velocity. The person here had a broken arm. And what that person would do is they would take the broken arm, which was in a cast, and they would place it right up next to the wheel. Like they're tired. I mean, they're hurt. So what the dealer didn't know and what the casino eventually figured out was that the guy had a microphone in his cast that was leading up his arm and down into a little computer in his shoe. And that microphone recorded the frequency that he heard towards and the frequency that he heard away. Because the one thing that they needed to have was the actual velocity of the ball. They couldn't just sit there and ask the dealer, hey, what velocity you're kicking this thing out? Because we're trying to cheat and get away with it. If we don't have the velocity of the ball, we're trying to figure that out. The other thing that they didn't have, and this was a very important fact, they didn't have the source frequency. The ball frequencies occasionally change depending on the material that they're using, the material of the ball, the material of the wheel. So the frequency would always change a little bit. So what they did is they didn't care about the source frequency. They knew for a fact that the frequency towards was frequency over 1 minus V over Vs. And they divided it by the frequency away. What have I taught you in physics? A lot of times, you don't have numbers because you don't need them. You don't need the source frequency of the ball to get the velocity, because if you divide one frequency by the other, that source frequency drops away. You could later figure out what it is, and in the homework you do, but in this particular case, they cancel. This problem can be applied to, we'll work on it. There's the great Walking Dead test that I gave about 2 years ago. There were a group of Walking Dead fanatics in my class, and we would always have our Monday meetings discussing the episode the night before, and they wanted a Walking Dead test. And the problem was Daryl on his motorcycle passes you on the street. You hear 1800 hertz as he's coming at you and 1400 hertz as he's going away. How fast is he driving? What's the source frequency of the motorcycle? This is the way that you can do it. And the first thing you do is you take the frequency towards over frequency away. And it doesn't matter. You can use away over towards or towards over away. Either way, it doesn't matter. So this becomes that. That's in the denominator of the numerator, it gets kicked down to the denominator. That's in the denominator of the denominator, it gets kicked up to the numerator. Now we solve for V. In this particular problem, the people, the students figured out the true velocity of sound in air upstairs in their hotel room. So they were able to get what V of S is. Now we're looking for V. How to do it? Cross multiply first. That comes up, that comes up. Distribute. And you all should be able to work through the steps for this. I want my V terms on one side and my non-V terms on the other. That's towards. Factor out the V over Vs. Solve for V. And so that's the velocity of the ball. If you're given the frequency towards and away, and you know the velocity of sound in air, you can get the velocity. So how does this work? You know that theta equals theta naught plus omega naught t plus 1/2 alpha t squared, and omega equals omega naught plus alpha t. They figured out that they needed to know the amount of time that this ball was in play. And so omega minus omega naught is equal to alpha t, and omega minus omega naught over alpha is equal to t. They figured out how quickly balls decelerate. They figured out the alpha. They figured out the omega at which the ball falls. That's the decay of the speed of the ball. What this does, V is equal to omega naught R. They knew the radius of a roulette wheel, so V over R is equal to omega naught. So they took this V and they plugged it in there. From there they got omega. From omega they got the time that it took for the ball to fall. Now remember, theta naught, which as far as 213 is concerned, is only 0. But when you're playing a roulette wheel table, theta naught is the initial position of the ball. Which slot is that ball in? Is it 2 red? Is it 13 black? Whatever. So they have that number. And now that they have V, they can figure out omega naught. They have the initial position. They have the initial velocity. They know what the radius of a roulette wheel is. They figured out the decay of a roulette wheel table because they were up in their attic for months figuring it out. So if you knew where the ball was going to be placed, when it was going to fall, you can predict not necessarily the specific place where that ball was going to land, but you could predict which side it was going to land. And what they did is that they changed the rates that they had were, roulette wheel table is 52 to 48 in favor of the casino. And what they did is they changed it to 40-60 in favor of the player. That's a significant advantage. That's an advantage that means only one thing. Dollar bill, yo. So, with physics, physics can do stuff for you. It can make you money. Now, granted, these people were cheating in a major league way, and they're probably, if they continued, would end up underneath the desert somewhere. So, this is an awesome way of understanding how physics works. It's an awesome way of understanding why this class is important for you, because they were faced with a particular problem. They did not understand the source velocity of the ball, but they knew the frequency towards and they knew the frequency away. That was all they needed, and then they solved it. So it's a very good problem. In terms of what's your bottom line, because this is all entertainment from now on, you need to get to that part and be able to understand it. This part here is just fluff for just to let you know how awesome physics is. Let's say, for an example, in the Darrow motorcycle, this will be the last thing. In the Darrow motorcycle, you hear the frequency towards is 1800 hertz, and the frequency away is 1200 hertz. This dude may be going really fast. What is the velocity of Darrow? What is the source frequency? The way that you would set up the problem is this. And you would go all through the steps to get this right here. Be able to derive it. Do not put "and a miracle occurred," poof, there's the answer. So let's just say, for an instance, we did this and got this. Well, the velocity is 1800 minus 1200, 1800 plus 1200, 350. So 600 divided by 3000 is 1/5. 1/5 of 350 is 70 meters per second, I think. Yeah. So Darrow's motorcycle is traveling at 70 meters per second. The frequency that you use, you can either use towards or away. In this case, I use towards. Why? I don't know. I just randomly picked it. 1 minus V over Vs. That's the frequency, moving source towards. And this gives you frequency towards 1 minus V over Vs is the frequency. Frequency towards, I gave you 1800. 1 minus 70 over 350. And that gives me the source frequency. 1 minus... Oh, wait. 1 minus 70. Gives me 1440 hertz. And so that's a solution to the Walking Dead Darrell motorcycle problem. And so that's all we need to talk about. We're going to do review for homeworks and tests tomorrow and Wednesday. Test 3 is on Thursday. Thank you.